Okay, thyristors are anything that that have more than 3 levels of doping associated with them. So if I have an NPN transistor or a PNP transistor, those are transistors. If I have 2 levels of doping, those are diodes. Anything with 4 or more fall in the now how can you have Thry, right? That's obviously 3. How can that be 4 or more? You know, you got to be Greek or something, right? So first thing we have is a silicone unilateral switch. SUS. Yeah, so there we go. We're going to put 4 layers together, and we're going to have a funny thing there. And this thing is going to turn on and off, and that's the whole point. We can look at it and break it apart, and it's sort of like 2 transistors, one going one way, one going the other way. So there's a PNP guy and an NPN guy. But when we put them together, it's going to do something weird. And what I'm going to do is when I turn on, I'm going to have some negative resistance characteristics. See that curve there? It has a negative slope. So it's going to have a negative resistance when I turn on. And turning on, that's an important thing to do, right? For switches? Yeah. Relatively important. It'd be nice if that graph was better looking. There's some holding current to keep it on. If the current falls below the holding current, it goes back to being off. Okay. Not used in nuclear weapons, so don't worry about it. It can be driven into cutoff. We look at it. If we're looking at it as I'm on or I'm off. And it might be in a series application, or it might be in a shunt application. So we have some peak voltage that happens. As long as the signal is less than that peak, it doesn't turn on. It has reverse blocking characteristics. It has forward operation only. But it can break down. All right, good enough. Next, it does have a negative characteristic part of the curve. This looks sort of like a diode. So, and if I get to the breakdown region, I melt it. Okay, so I don't want to do that. But forward biasing, I turn on, and everything's fine. If I change the temperature, I'm going to turn on at a different point. That's not relatively good. I put this in some spacecraft that goes up to where the temperature is not all that warm, and it's doing something that I really didn't want it to do. So that's not a good thing. Silicon-Controlled Rectifier, an SCR, 4 layers of doping again. We have a gate, an anode, and a cathode. We trigger the SCR through the gate. Again, we think of it as 2 transistors. Now, I look at those 2 transistors and I say, well, that's the same configuration as that silicone switch thing I was just looking at. What's the difference? And the difference is how I make it. So I made this guy to do something different. I have characteristic curves that are about the same. I turn on my silicon-controlled rectifier and SCR. I have in the reverse direction, it looks sort of like a diode. And if I change the current, something's going to change the temperature. What I'm going to turn on changes. I have some holding current that turns it on. Normally, a silicon-controlled rectifier is being used in an AC circuit so that when I pass through 0 on the negative half cycle of the AC wave, it turns off. Okay, so this guy's going to turn on in the first quadrant, stay on until we cross through 0, going at 180 degrees in our sine wave, and then it'll turn off for the 3rd and 4th quadrant. We have some how fast can it go calculation, and it has some surge current that it's going to be able to maintain safely, and then above that surge current it's going to just burn up on us. We have negative gate triggering, but we could have a false trigger. So the sun could throw down some cosmic rays and trigger this thing. The temperature could increase and trigger this thing. I could have a change in voltage across it that triggers this thing. So I could have false triggering going on. Probably not a problem if I'm using it in my house. Might be a problem someplace else. So if my change in voltage, change in time is too big, I could have a false triggering. We prevent the false triggering by not allowing those large changes in my signal. So we could plug in an RC circuit there. The RC circuit is going to prevent fast changes to the voltage. Oh, I guess I should go to my office and get my car. No, I go towards the door. Now that they're there, I can sing my song because I have a good voice.
Yes.
Yeah, unfortunately, it's a tenor thing, and I'm only doing bass. All right, so now we're gonna have some Zener diode providing some voltage to the SCR, and I'm gonna be turning it on. This is showing it in a DC application. Normally we don't put an SCR in a DC application. So that's okay, we can handle that. We're gonna have a critical angle which is gonna turn this thing on. So if we look back, we can't look back. Because if this were an AC power supply, then I would have a different voltage ending up here as I'm changing the AC, and the angle will turn it on. The angle of the AC. But I have a DC application there. So here we are. Now we got an AC power supply, and I'm gonna change the angle at which the point at which this guy turns on, and I can only turn on between 0 and 90 degrees, because past 90 degrees I already passed the point where I would have turned on if I was going to turn on. So this guy only is going to turn on in first quadrant. He's going to turn off after the second quadrant, and he's not going to be on at all when I'm going negative. Diacs and Triacs. Bidirectional transistors, not transistors, Thyristors. They go in both directions, whereas the SUS guy and the SCR are only going to operate in the forward direction, positive voltage direction. These guys work in both directions. So I go and I have 3 pieces of doping associated with them. Got a funny looking symbol that's associated with them. And depending on how I make them, they will turn on at a particular voltage. So a diac is going to turn on in the first quadrant at 5 volts, or 10 volts, or 15 volts, or 12.73 volts, depending on which one I buy. So I have a huge variety of them, and I buy them to turn on an SCR or to turn on a triac. That's what I get them for. They have a turning on characteristic in both directions, both the forward and the reverse direction. Then they operate in both forward and reverse direction. So this would be a first quadrant turn on, that'd be a third quadrant turn on. When I look at the doping of that guy, I see, oh, this is a triac. So now a triac has 1, 2, 3, 4, 5, 6 different layers, 5 different layers of doping, and gates hooked up at various spots. And now this guy will turn on in all 4 quadrants. So depending on who is positive and who is negative, the main terminal 1 or main terminal 2, and whether the gate is positive or negative, I can turn on in all 4 quadrants of an AC signal, and that makes things even better for me. I have a characteristic curve that looks like that. First quadrant, if MT2 is positive and the gate is positive, I turn on. Second quadrant, main terminal 2 positive, gate negative, I turn on. Negative and negative, third quadrant, I turn on. Negative, positive, fourth quadrant, I turn on. Do I memorize that? No, I don't memorize that. But what I do know is that it's going to turn on in all 4 quadrants, so that I could use it that way. The current is obviously flowing in the wrong direction because the transparencies are electron current. The current's obviously going to have to be flowing in the reverse direction from the arrows are. We control it with voltage at the gate, plus or minus 0.9 volts. It doesn't take much to turn it on. We can use a diac or a diode to get that voltage on the gate to trigger it. So we have triacs turn on first and third quadrant. We have triacs that turn on in all 3 quadrants. Our operating curves are about the same. Next thing, Unijunction Transistors. 3-terminal switch device which triggers voltage that's proportional to that applied. So as I increase the voltage, I get better voltage going across it. Some formulas which I hope we'll never have to use: intrinsic standoff ratio, telling us what the voltage across the device is. I only have 2 things of doping. I have a little bit of P and a lot of N in the construction of this guy. And the currents are going in the wrong direction again, so that's good. But that's my operating curve. Really funny looking. And I have a negative resistance part of that operating curve that is very large. So now I can go and really mess up somebody bad with that. So I've got a unijunction transistor that's turning on the SCR, and now I'm turning on the SCR in the third quadrant. Discrete photodetectors. So every single diode, transistor, SCR, triac, right up the line, I can trigger them with light. So instead of triggering them with electricity, I could trigger them with light. All right. So, and normally I use anywhere in ultraviolet to infrared. Infrared's always nice. I like that one. We have some wavelength associated with our light. The wavelength is C over F. What I do is wavelength is in meters, basically, nanometers. Speed of light, 3 times 10 to the 8th. Why would they put it in nanometers? Why would you put speed of light in nanometers per second? Well, that doesn't make any sense. And the frequency of the device. What I do is I think of the speed of light as in meters per second, and frequency is in per second, and wavelength is in meters. So if I forget that formula, I can just do a dimensional analysis on this. Light has some intensity, and what I do when I have, this is a photodiode, So I have a signal coming in, making some light, and then the light turning on the diode. And when I do that, what I've done is I've isolated completely the signal from the rest of the circuit. So the signal coming in is isolated from whatever was happening on the other side. I can buy these things 8, 16, 32 at a time sitting on a chip, and it works quite well. So photodiodes might look like that, might look like that. When the light beams are going away, that means it's a light emitting object. When the light beams are coming towards, that means it's being activated by light. I can have phototransistors. So here's a phototransistor. I've got a light emitting diode sitting there, emitting some light, turning the transistor on. So I can do that too. In fact, I can do just about anything, if I think about it, it can be done probably. Has been done. Darlington pair. I have a light emitting, I have a photodetector Darlington pair. So the light turns on the first transistor, which turns on the second transistor, which allows maximum amount of current to flow. Light activated SCR. So I don't necessarily have to have a gate. I can light activate it. Optoisolators and Optointerrupters. So optoisolator device that uses light to couple the signal from the original thing, and optoisolators, they isolate the voltage. And I have a whole set of either ones of those that I can buy and throw into things. The optoisolator has 10 to the 11th ohms. Wow. 100 giga-ohms? I guess that's enough. That'll keep me away from you, right? Yeah. Can't shock you very much. An optointerrupter, an IC optocoupling designed to allow external objects to be blocked, to block the light path between the two guys. Alright, that's what they look like. That's how I'm going to buy them. I can have Varactor Diodes. So these guys are going to vary the capacitance of a circuit. So the voltage of the circuit across the diode is going to cause the capacitance to change. And if you think about the filtering things we had earlier, if I can change my capacitance, I can change the tuning frequency of my filters, right? If I had a bandpass filter, I couldn't do that. So here we go, all the way up to the awesome 100 picofarads, depending on what the voltage is across the diode. And here we have an application, and it's a tuning circuit. So I have a LC tank sitting there, LRC circuit, but this guy's variable, so I can tune it to a different frequency. Transient suppressors. So now I have some surge voltage that happens, and I want to stop it from destroying my gear. I don't know why. You better just to replace it. Okay, so I throw in a bunch of diodes, and they're gonna stop the surge. Throw in some surge protection to protect my power supply from surges. And the transient suppressors, depending on temperature, will depend on what the peak is going on. So I have back-to-back suppression. So instead of having two separate diodes, I can have one diode in a surge protection circuit. called a back-to-back suppressor. Then we can have tunnel diodes. Tunnel diodes have a negative resistance region. A regular diode does what the black guy does. A tunnel diode does something different. We use them in microwave frequency applications. And we use them because of the negative resistance that they do have. They act like a switch, but a little different. So here we have a tunnel diode sitting somewhere, some negative resistance oscillator. So making oscillations for us. Oh, we're done? Is that all there is? Didn't even make it to the hour? Okay, so there's a request that I go back and solve problem number 25. Is that the one? Oh, I remember doing this. This one's easy. Yes, we just ran out of time.
There's one more part of it.
There's one more. I got it.
One more.
It must be done.
Chapter 25, number 25. All right. We have a plus 5 volt regulator. Okay, so I'm plus 5 volts. I got 2
Well, we
ohms.
started, but never finished it.
And IL goes between 0 100 milliamps. We want to express load regulation in volts per milliamps, in percent, and in percent per milliamps. That's what we want to do. All right, well, I guess we'll do the volts per milliamp first. 5 volts per 100 milliamps. Should we change that? 50 volts per milliamp. All right. Then we want to go and do it in percentage. Well, if I have 2 ohms and I have 100 milliamps, then my change in voltage can be 2 volts. My change in current can be 100 milliamps. So that's going to be a percentage of 20%. That looks like 20%. And then if we want percent per milliamp, I wonder what the difference is between percent per milliamp and the other guy.
Wait, isn't the first part wrong?
Oh, I hope so. Why?
Because on 883, it tells what the regulation rating of 2 ohms means.
See, that's what I figured you guys would do. You'd figure it out and tell me what the problem was.
It's VMA. VMA expresses resistance value.
Oh.
You multiply
Well,
that times by L, it gives you
yeah.
VL value.
I think that, oh, so you want me to go 5 minus 2 volts. Is that what you want me to do? Yeah, I think that's probably what you want me to do. And then that becomes 3. No? You don't want me to do that?
I don't know how it's actually done, but that's not.
Yeah. On page 883, load regulation in volts per milliamp would be the no load voltage, which would be 5 volts, minus the full load voltage. Full load voltage would be 100 milliamps going through 2 ohms, would be 2 volts. So that'd be 3 volts per 100 milliamps. So it'd be 30 volts per milliamp. Is that better? Maybe that's better. And then a percent, the total percent change in the output voltage over the rated range of the load currents. Alright, so the voltage changes by 3 volts and the current changes by 100 milliamps. That still looks like 30% to me. I'd go with 30%. Percent per milliamp. I'm looking at page 83. The percent change of the output voltage per 1 milliamp change in load current. Okay, so if I had 1 milliamp, my voltage would change by 0.02. So I have 0.02 volts per milliamp. So that, percentage-wise, 2% per milliamp. Well, we'll go with that. Unless you want me to try it again.
Can you go back a little bit, please?
I'd rather not. No. Well, I guess I should. You know, on a scale of 1 to 10, you know, I'm about a 3 on whether or not any of those are right.
Thank you.
If you say so. Not yet? Oh, you're goofing off doing something over there. I'm going to go to page 939.
Okay.
And see if there's any reason on earth to believe I can do problem number 3. Okay. So now I'm on chapter 26, number 3. So I've got a SCR, and I have a fuse rating of 2.6 amps squared seconds. Determine the maximum allowable duration of a 50 amp surge through the device. I sort of remember that formula. Alright, so let's find the SCRs. Okay, I found the SCRs. And the time max. What am I supposed to be calculating anyway? Determine the maximum allowable duration. Okay, so that's on page 912, where it says T max is equal to I squared T rated divided by IS squared. Alright, so I'm going with the 50 amps, 50 squared, and T rated. That probably means I have to go and find it someplace.
It tells us the fuse rating is 2.6.
The time duration of the surge.
The problem gives us both numbers. It gives us the surge and the rating.
But it doesn't give us, we need three things. Oh, right. Gotcha. No problem. Gotcha. All right. Pay attention, Doug. 2.6 amp squared seconds. So that's everything that's on top. That guy there. And I'm going to divide it by 50 amps squared. And then I'm going to take out my calculator. Oh, I can't take out my calculator. I didn't bother to bring it. Bummer. Well, it doesn't really matter. I got one over here.
You just have it in your phone.
I did? Oh, there it is. I see it. I was hoping I didn't have it. 2.6 divided by 50 squared. 1.04 micromilli. 1.11. We'll call it 1 millisecond. Okay, that was easy enough. Number 17. A photodetector has a value of lambda s, 0.94 nanometers. Determine the optimal operating frequency for the device. Okay, so the speed of light, which is in meters per second, is equal to lambda times the frequency. Lambda is in meters, and frequency is 1 over seconds. Okay, so that's the formula we're going to use. So F is the speed of light, 8 times 10 to the 17th nanometers. That's so ridiculous. 0.94 nanometers. Speed of light per second. All right. I'm all set. I think I'm all set now. 8 doubly 17 divided by 0.94. I don't believe it. 8.5 times 10 to the 17th hertz. How can that be right? Determine the optimal operating frequency for the device. Well, I guess that's it. Does that seem big to you?
I think it's supposed to be a 3 instead of an 8.
Oh, yeah, you're right. Picky. Front row's being picky on me. Got the wrong speed of light. Alright, so we'll do it again. 3 divided by... How did I do that? Never mind. 3 divided by 0.94. Okay, so we'll call it 3.2.
That's what's in the back of the book.
Oh yeah?
Yep.
Bummer. The author got one right?
Yep.
I hate it when that happens. Alright, well, I guess I don't deal with speed of light and frequencies around the speed of light very often, so that's why I think it's too big. Number 20. You guys don't move that fast, so it's not a real issue. 25. A first order bandpass filter. Okay. R is 33 ohms. C is 0.33 microfarads. Draw the frequency response curve for the circuit. first order bandpass filter. R is that. Well, if I do this, then I'm going to have a low pass filter. And if I do this, I'm going to have a high pass filter. And the the problem doesn't say which one I've got. That seems pretty weird. That seem weird to you? Luckily, we do have a Bode plot that we can use to plot the curve for us, and we won't have to worry about it. Okay, so okay, there we go. So what do we need? We need an AC power supply. 1, 2 of them. We'll need a couple grounds. 1, 2. Probably don't need any more than that. And then we need 2 resistors and 2 capacitors. Oh, I found the capacitors. We'll put one there, and we'll put one over here, and then we'll put a resistor. Put one there, and one over here. Yeah, that's perfect. We'll rotate this guy a little bit. Maybe we'll rotate him, who knows. And we'll rotate that guy a little bit. Okay. Excellent. And we'll hook him there. Does it matter what the AC power supply is? The answer is no, it doesn't. Doesn't matter because why? All we're doing, the Bode plot is just going to go in and put whatever it wants in anyway. All right, so we'll go the input there to there, the output there to there, input. Do I have enough wires yet? All right, now, capacitors are 0.33. Thank you very much.
You're welcome.
Thank you. That's just so wonderful. I love it.
You can just find you and then function. 0.33 U.
There. 3, delete 3. So I got it? All right, let's see if we can do better on this one. All right, so did I get the frequency right? 33. Wrong one. Alright, so before we do anything, what's the critical frequency? The critical frequency is going to be 1 over 2 pi RC versus the square root of RC. We have to go back to chapter 23.
That's the square root.
Square root of RC. Yeah, I knew it. 2 pi square root of R. No,
Now you have 2 pi RC.
no, it's 2 pi RC.
804.
804. Getting close. Yeah, 2 pi RC. Okay. So if I go 1 divided by 2 times pi times 33 times 0.33 double E minus 6, I will get the wrong answer, right? Because I hosed myself over and I didn't use parentheses. Okay, there we go. So my critical frequency is 14.6 K. So that's what I should see that in my, that's where the 3 dB down point should be. Alright, so open this guy up, put in there, open that guy up, put in there. Log is fine. The frequency, this frequency is way too high, so we'll go kilo. We'll go like 50 kilohertz, and we'll go a hertz to 50 kilohertz. And the dB range is about right. And this guy here will do the same thing. We'll go 50 to a hertz, and why can't I have a different screen? All right, we'll turn it on. There we go. Well, isn't that just lovely? Totally and completely lovely. So we'll bring this guy over and find the 3 dB down point. Way to go, can't even find the 3 dB down point when looking at it. Okay, so that's about 3 dB down. And that's 14K, exactly what we thought it would be. And on the other side, we find the 3 dB down point. Like I'm losing control. Yeah, that's about the same spot. So then we'd go in and say, okay, be that way. We'll go in, change this to minus 100. Change this guy to minus 100. And then we have a better curve. Okay, and then we'll change this guy to 1K. And this guy to 1K. And oh, that looks good. We'll change this guy to 10. Oh, that's much better. Much better curve. Much better curve. I'm going to change that guy to 10. All right, there we go. Now we're going to go looking for the 3 dB down point. Just piss you off. Alright, there we go. Found that one. And we'll find the 3 dB down point on this guy. Okay. 14.58 kilohertz. What do we calculate it to be?
14.6.
14.6? I guess that's good enough. Is that good enough? What happened to this guy? He moved. There you go. 14.58 and we calculated 14.6. Did we do what the problem said? Draw the frequency response curve of the circuit. So one could suggest that we didn't do what it said to do, right? because we didn't draw anything. All right, so this guy here is the first guy. So we'll draw it. Frequency response curve of the circuit. And that happens at minus 3 dB, which is 14.6 K. And then we'll draw this guy. And we'll draw him like that. And 14.6 kilohertz, minus 3 dB. Good enough? Now we did what it said to do. Alright. Alright. That means